the trapezoidal rule of integration says that between the limits of integration a to b, we assume a straight line instead of the real function, and this makes the area under the curve as the area under a trapezoid shape, which is a combination of a triangle and a rectangle. So the area then turn out to be the width time the average height, f of b plus f of a divided by 2. Since this is a crude approximation, divide the function into several segments, and by segment, we apply the trapezoidal rule. So this helps us to define the summation like f of a plus 2 times the function values at the interior points plus f of b, which is the right end point. So this can be programmed, and generally we program it with the equidistant points. So we define the delta x, like in this algorithm, we define delta x b minus a over n. In this algorithm, which is written in the form of a pseudocode, this is one of the styles of writing the computational logic or the algorithm. So we have to provide the values of a, b, and n. N is the integer, represents the number of segments you assume during this calculation. Then we define the delta x, b minus a over n, so that all the points x naught to all the points from x naught to xn, they all are equispaced and they have the common difference of delta x. We transform this logic to Fortran program where the function, a real function, has been defined here. This function is 1 minus x squared. This will be called to compute f of a, f of x1, x2, x3, and all that. In the main program, we have the implicit none, and we have declaration of variables, and then we defined inside the program a, b, and n, and then we define the delta x, then the summation to compute the approximate value of integral. So f of a plus f of b divided by 2. And for interior points, this is the repetitive calculation. New point is generated by a times a plus I times delta x, since points are equidistant. And then on every new point, we have generated calculate new point, and then compute the function value from it at the end of the loop. And finally, with all the values of apps variable, multiply delta x to get the final result. So let's save it and run it. So this is our working directory in D folder. So I write the compilation command calculation of integral dot for minus o calculation of integral dot exe. Computer is silent. It seems to be working on it, and yes, it has returned. It seems to be no problems in the program. So if I run it, so with the fixed values of a, b, and n, and the integral, it is very close to the real value. We know this analytical answer for the problem. So for this one, if you increase the number of points, right, this is really an important thing to consider, that how many calculations you are sufficient to get a particular level of accuracy, is the values are changed within the program, therefore I have to recompile the program, right? So therefore it is recommended to make it generic and read the values on the go, the read statement and so on. So there are no problems, and now the answer is even more better. Now the next thing is to develop generic programs. So this is all the calculation from here, from this point, a, b, and n. Having the values of a, b, and n, there's a delta x calculation, there's a traps calculation, there are further calculation up to this point. Right? So these are going to be the elements of the function. So I copy this one from here and say x. Now this part of calculation is not there. So I define, we can use this one over here, but let me use new file, a separate file, right? I call it, this is my functions library file, right? Let's suggest a name for it for our reference. So I call it computing fundamentals library.for will be its name. The first program in this library is for trapezoidal rule. So I have copied the part of calculation, and this requires certain variables and function name. So let me call it the function. Well, it should, as a convention, from the 7th column, I call function, and I say traps function. It requires inputs a, b, n, and the function as well, right? These are the variables that we use in this function. So now let's define them properly. So it should get real values of a, b. First get the integer value of n, and the output of the function traps. That was defined as a summation, right? So here we have delta x calculation while getting the values of a, b, n. There is f, there is delta x, and all the calculations. And finally, in the function structure, we write return statement. And finally, the end function. End function traps. So I copied the part of the algorithm from our earlier program, and I set that into a function structure, right? And then let's save this one in the same directory. Fortran file. So cf library.for. cf library.for. So some of the text has been highlighted. And now let's do the like joining of the program and the library. So call int. There is the function that you require in main program, right? So it is f of x. Generally, I prefer to change the name, but at present there won't be a problem. But okay, f of x. Here we have the values. Now the function f to be recognized in the function library. We set an attribute, a name external to f, right? So that it would be taken as argument in the function, right? So it should be recognized as a function in the argument of our traps function. So there are definitions of A, B, N. We can read them. So everything is fine, right? So now let's compile it and run it. So I have set a new line external function so that the function which is written here would be recognized by our library. So now the command. Now E77 call integral dot for. Also we have to compile the library cf library dot for minus o, and then the name call integral dot exe. Behold with silence, no cry, no sigh. So all int.exe has been generated. So from the main program, and libraries are going to be linked. And now I call the function, the main program. So wow. So something strange has been returned. Let's check where is the inconsistency. Okay, I'm going to check first the function traps. Okay, traps has been computed. Traps has been computed. Okay, well, this variable, this is a function. It requires the variables A, B, and all. We have not used that function. So traps A, B, N, and F, the external function, right? Traps. Still, there is some inconsistency. Real traps, external F, traps A, B, N, and F. F function. I here library delta x and others, they need to be defined. So delta x and integers I traps. But what was the real xs and f? Okay. Let's look at the error again. Undefined reference to traps. Okay. F, the reference was missing. Okay. Still, we need to work on it. Delt x, f of a, f, real, traps real, I, a, b, delta x. Okay, the compilation command was not correct. So let's do it again. Oh, yes, this is the command that we have to look for. Right. So it has been rightfully compiled. But we have to see the answer. Actually, the answer like 10 raised to the power minus 39. This is the value when something is not initialized, something is not computed, and the value is called for. So let's run the program call int.exe. So now the answer is fine. Do another change. Now in the main program, I define another function, right? So I define here another function g of x with the real x g, and I return a value sine of x, one of my favorites. Well, this is favorite of many uh, scientists and mathematicians. Then n function e. Now let's calculate the integral of this one as well. So we know we have to define it as an external function, right? Now I'm going to do the integration int asterisk the integral of function g of x is perhaps for a I say 0.0 real number, for b I say 4.0 times a tangent of 1, so it will be pi by 4. So from 0 to pi, sine of x is going to be integrated with the say 10 steps. F external is g, right? Fair enough. And well, in which column we are? Oh, it is column 83. We cannot write this one beyond 72 column, right? So I require a continuation mark in column 6. Let's see whether it will work or not. So sine of x when integrated from 0 to pi, we know the answer. It's close to 2. The main program was changed, therefore we have to save it and write. So the continuation mark has been rejected. We have to use something else. So with the continuation mark, I'm always a bit uncertain. Well, this should be in column 6. Okay, with 1, hopefully it will work. So the answer says that the error says that one. So library and this one, this is fine, right? Behold, two integrals are going to be computed in our main program, taking the algorithm from the library. And here we go, 1.98, and that's it, right? So now we have learned the strategy to develop the programming libraries. And this type of generic libraries where the functions can be used as arguments, that was the thing that was worked out by the numerical programming companies. The NAG is an example. IMSL of Intel is an example. So with this example, I hope that my students will be able to use the NAG libraries if they are available, and they can interpret what's going on in those libraries.